Welcome to The Explainer. Today, we're digging into a really fundamental idea. A material's real-world behavior, whether it bends or just snaps, is all decided by its invisible internal architecture. To really get why, we have to start at the atomic scale and build our way up. No, that's not from a movie script. This actually happened. On a calm, cold day back in 1943, the SS Schenectady, a huge, brand-new steel ship, literally cracked in half while it was just sitting at a dock. So how in the world does that happen? How can solid steel just fail like that? Well, the answer isn't just about the kind of steel they used. It's all about its hidden internal structure. To solve this mystery, we need to zoom in like way, way in. Let's get into it. Okay, so at the very, very heart of any material, I don't care if it's a steel plate or the glass on your phone, everything is held together by forces between atoms. And these forces, they're the first and most fundamental level of its structure. You can think of these primary bonds as the fundamental glue of materials. The specific type of bond is what determines a material's most basic characteristics, things like its melting point and just how stiff it is. Now, while all three of these are super important, for the kind of engineering materials we're talking about, like the steel in that ship, we're really focused on one in particular, the metallic bond. It's this unique arrangement where atoms share a whole sea of electrons, and that's what gives metals all their classic properties. So the big takeaway here is that these strong primary bonds are our foundation. They're step one. But what happens next? How do all these bonded atoms actually arrange themselves? That brings us to the next level up. Right, so we know atoms are held together by these bonds. But here's the cool part. In metals, they don't just form some random clump. Instead, they organize themselves into these incredibly ordered, repeating 3D patterns. Think of it like perfect microscopic scaffolding. Probably the best way to get your head around this is to picture a perfectly repeating 3D wallpaper pattern, but instead of some floral design, you've got atoms. This kind of long-range order is exactly what makes a material crystalline. And this entire crystal, which can be absolutely massive, is built from just one simple repeating block called a unit cell. It's the basic blueprint that just gets copied over and over and over again in every direction. And here's a great example. This geometric setup, with an atom at each corner and one right in the middle, is the blueprint for a lot of steels. So this is the second level of our structure, built directly on top of the foundation of those atomic bonds. Now, let's be real. An object like a steel beam isn't just one giant, flawless crystal. The reality is actually much more interesting. Let's zoom out just a little bit to the microscopic level. Imagine a big box filled with perfectly stacked Lego blocks. But here's the catch. Each block is angled a little differently from its neighbors. Every single one of those blocks is like a tiny crystal, or what we call a grain. A real piece of metal is made of millions of these things. These boundaries are where the perfect, repeating patterns of two different grains smash up against each other. It's a region of total atomic chaos, a disruption in the pattern, and believe it or not, these messy little regions are incredibly important. This probably sounds completely backward, right? How can a disruption in a perfect pattern actually make something stronger? Well, it turns out these boundaries are the absolute key to controlling how a material behaves when you put it under stress. This image shows us exactly why. See, when you try to bend a piece of metal, these tiny imperfections called dislocations try to move through the crystal. But when they hit a grain boundary, bam! It's like hitting a wall. The dislocation can't just cross it, so it gets stuck, and you get a pileup right behind it. So here's the bottom line. The more boundaries you have, the more walls you have to stop those dislocations from moving around. This means a metal with lots of small grains is generally stronger than one with a few big grains. By controlling the grain size, engineers can literally dial in the strength of a metal. Okay, so we've gone from atomic bonds to crystal structures to entire communities of grains. Now, let's connect all of these different scales to the properties we can actually see and measure out here in the real world. There's one more layer of structure called a phase. The easiest way to think of this is like a salad dressing with oil and vinegar. Yeah, they're both liquids, but they are chemically distinct and they don't really mix, right? In metals, different phases can have different crystal structures or different ingredients, and mixing them is a key way engineers create alloys with really unique properties. And this right here is the central idea of all of material science. The way you process a material controls its internal structure, and that structure is what dictates its final properties and performance. It is a direct chain of cause and effect.
So, what we've really done is just climbed this ladder of scale. We started with the tiny forces holding just two atoms together, built up to those repeating crystal blueprints, then to the whole community of grains, and finally, we arrived at the overall strength of a massive steel plate.
Which brings us all the way back to our original question. Now we can finally answer it. After the failure, investigators took a close look at the steel, and all the evidence pointed to something called intergranular fracture. On that very, very cold day, the steel's microstructure became brittle. And those grain boundaries, the very same regions that normally provide strength, they suddenly became a path of weakness. A crack formed and just unzipped the ship right along those microscopic seams. Understanding this whole hierarchy, from a single bond all the way up to the final product, is everything. It lets us not only prevent failures like the Shinadi key, but it lets us ask a much bigger question. How can we design materials from the atom up to build the innovations of the future? Thanks for watching.